Okay, hello. Sorry, I had.
Sorry, something's not right. Wait a few minutes and try setting up again. You can also try unplugging your device and
Okay.
plugging it back in.
So sorry, I had to make a second part to this. And I also realized that you couldn't see the bottom of the other video. So here it is. I'm sorry. Okay, so for the second part, the 15 and 16 are also independent events. So like we're going to be like solving it like how we did for number 13 and 14. We're just going to be multiplying each scenario, each event by itself. So for number 15, in this case there are technically 4 scenarios because there are 4 different questions. And in each question, she has the possibility of either choosing true or false, which would give us a probability of 1/2. So we would multiply 1/2 by itself 4 times to represent the 4 different questions and the fact that she can only choose one or the other. She can only choose true or false. So then that would give us an answer of 1/16. And then for problem number 16, we would multiply 4/52, which would represent the deck of cards and the probability of drawing a king. So like in a deck of cards, we have 4 kings, and the total amount of cards that we have is 52. So it would be 4/52. And then we would multiply that by 2/10 to represent the letter I, the probability of getting an I. So in this word, incredible, there are 2 I's, and the total amount of letters that this word has is 10. So it'll be 2/10. And then this, we can simplify it into 1/13 times 1/5, which would give us 1/65. So yeah. So then moving on to number 17 to 20. These are also independent events. However, it gives us like multiple I guess scenarios. So it says a bag contains 30 lottery balls numbered 1 through 30. A ball is selected, replaced, then another is drawn. Find each probability. So we know that these are independent events because it says right here that the ball is being replaced. If it was dependent, it's going to say that it is not replaced. So like for number 21 through 24, the ball is not being replaced. So these are going to be dependent of each other. But since number 17 to 20 are independent events, we are just going to figure out each of the events and then multiply them by each other. So like for number 17, it says the probability of taking out an even ball and then an odd ball. So we know that like if we divide 30 by 2, we're gonna get our even and our odds because they're like half of each other. So it's gonna be 15 over 30 times 15/30, which we can simplify it into 1/2 times 1/2, which would give us 1/4. And then for number 18, it says the probability of getting a 7. So we know that we can only get 1 7 from in a list of 1 through 30. So it would be 1/30. And then we're gonna multiply that by 14/30 to represent the numbers that are greater than 16. If we subtract 30 minus 16, it's gonna give us 14. And those are the 14 numbers that are greater than 16. So then we could simplify that into 1 over 30 times 7 over 15, which would then give us 7 over 450. And then for number 19, it says the first scenario, I guess, says that we take out a multiple of 5. So we would divide 30 by 5, which would give us 6. And those are going to be the 6 numbers that are a multiple of 5. So we would write 6 over 30. And then we would multiply it by the number of prime numbers that there are. So there are a total of 10 prime numbers between 1 and 30. So we would write 10 over 30. And since these are independent events, we would continue to write the 30 as the denominator, because 30 is still the total amount of balls that we have, since the balls are being replaced. They are being like put back into the probability, or like into the basket. Like let's say the basket, let's say the balls are in a basket, like they're being put back after being taken out. So then for number 19, the fractions could be simplified into 1 over 5 times 1 over 3, which would give us 1 over 15. And then for number 20, it says the probability that we get 2 even numbers. So we know that there are 15 even numbers in the list from 1 to 30. So we would write 15 over 30 and then 15 over 30 again, since we want to get another even number, which would give us the exact same thing as number 17. So then for 21 through 24, these are going to be dependent events, which means that our second fraction is going to depend on what our first fraction is, especially the denominator. So like for number 21, our first scenario or our first event is to take out a 2-digit number from the lottery. So we would have to find out how many 2-digit numbers there are from 1 to 30, and that is 21. There is 21 numbers between 1 and 30 that are 2 digits, that have 2 digits. So we would write 21 over 30. And then for the second event, it says to take out a number 4. So just like for which one was it? For number 18, there is only 1 4, like how there's only 1 7. Just like how we have only 1 7, we only have 1 4, so that would give us a 1, like as our numerator. But our denominator is going to be 29, because we already took a ball out. So now we only have 29 balls. So like how it says here, that it says the ball is not replaced, it means that we're taking one out and we're not putting it back in. So that brings our number down to 29 from 30. So yeah. So instead of being 1 over 30, it's going to be 1 over 29, because we already took one ball out. And these fractions can be reduced to 7 over 10 times 1 over 29, which would give us 7 over 290. So then the same idea would apply to 22. So we only have 119 in the list of 1 to 30. So it would be 1 over 30, because we still have our 30 balls and there's only 119. So then that would be multiplied by 7 over 29, because there are 7 numbers that are a multiple of 4, that are multiples of 4, meaning that they can be divided by 4. So like the multiples would be it would be 28, because it can be divided by 4, and like so on and so forth. So like to find that out, you would basically just divide the 30 by 4, and that gives you like the amount of of multiples, the amount of numbers that are a multiple of 4 that we have. Yeah. So then the denominator would be once again 29 because we already took out one ball. We already took out the 19. So that would give us 7 over 870. And since these cannot be reduced, we would just leave them like that. So then for number 23, again, there's only 124, so it would be 1 over 30. And then it's asking us for the probability of a number less than 15, of taking out a ball that is a number less than 15. So that would be, there is going to be 14 numbers that are less than 15. So our top number would be 14, and then our bottom number is going to be 29. Our denominator is going to be 29 because we already took out one ball. So then it's going to equal to, I'm pretty sure we cannot reduce 14 over 29. So it would just be 14 over 30 times 29, 870. And then 24, it says 2 perfect squares. So we would have to identify how many numbers there is between 1 and 30 that are perfect squares, meaning that when we square them and find their root, it gives us an actual number. So like a perfect square would be 4, because when we root it, it gives us a 2. And then another perfect square would be 9. When we square root it is 3. And then another one would be 16, because it gives us a 4. And then it would be 25 because it gives us a 5. And that would be it. From 1 to 30, we would have 1, 2, 3, 4 perfect squares. So it would be 4 over 30. And then we would multiply that by 3 over 29. Because we already took out a perfect square and we already took out a ball. So that would bring us down to 3 and then 29. And then that would equal to, we could reduce this fraction by doing 2 over 15, and then we multiply it by 3 over 29, which would be 6, and then 15 times 29, 435. And then for number 25 and 26, they're also gonna be dependent events. It's just that we have to figure out what those events are. So it says the football team has 5 freshmen, 8 sophomores, 11 juniors, and 16 seniors. If 2 are chosen at random to participate in the coin toss, what is the probability that both players chosen are seniors? Okay, so first we would have to figure out the total number of students that we have. So it would be 5 plus 8 plus 11 plus 16, and that would give us 40. And then, so it says, what is the probability that both players chosen are seniors? So our denominator for our first fraction would be 40. For the first time that the player is chosen, is going to be 40 because we have 40 students in total. And then we're going to have 16 on top because there is a total of 16 seniors. But then for our second fraction, our number is going to go down to 39 because we already picked 1 student out of the total amount of students that we have. And now we only have 39 students. 39 students in total to pick from. And then if we want a senior again, the number would also go down to 15 because we already picked the senior. So then now we would multiply them. 16 times 15 equals to 40. And then 40 times 39 equals 1,560. I think we could have reduced the 16 over 40, but oh well. I'm gonna just do it here in the bottom. It would be, if we divide by 4, let me see if we can divide 40 by 16. No, we cannot. So if we divide by 4, that would give us 4 over 10, but then we can simplify it again and make it 2 over 5. So it'd be 2 over 5. So then 2 over 5 times 15 over 39 equals 30 over 39 times 5, 195. Yeah. Okay, and then for 26 it says Ryan's mom randomly chooses 2 days each week for Ryan to do chores. Okay, so we have 2 days. What is the probability that she picks Saturday and Sunday? Okay, so we know that we have a total of 7 days in a week, right? And we are choosing 2. So 2 days each week for Ryan. Okay, so I'd read 2 over 7. And then we would multiply that by, since we already picked a day in our first fraction, since we already picked a day here, our other fraction will have a denominator of 6. And then we would have a 1 on the top. Since we already picked a day, we already picked Saturday or Sunday, our number would go down to 1. So then this would equal to 3 over 42. And that would be our final answer. So yeah, that would be it. As always, I hope this helped. I hope I didn't confuse you. And I hope you do great on the test. Yeah, bye-bye.